Hello friends, IBM is here to bring you another episode of Learning Physics. This is AS Physics 9702 multiple choice questions. I think this is part 7 of electricity and DC circuits. Without wasting time, I want to take you to where we stopped so that we pick up from there in this part 7. So I think in part 6 we stopped on page 141. And I want us to proceed from part 6 to the next. I want us to proceed to part 7 on the same page. So question 33, 4 resistors of resistance R, 2R, 3R, and 4R are connected to form a network. A battery of negligible internal resistance and a voltmeter are connected to the resistor network as shown here. The voltmeter reading is twice V. Note that the voltmeter is connected across 2R and is reading 2 volts. If the voltmeter is reading 2 volts, then we can predict the current in that part of the. Note that R3 and R plus R are 3R, 2R, and R are in series. So the current through them is going to be the same. Let's just use these 2 volts to find the current through 2R, and it will be the same current through 3R. It will be the same current through R. So the current this side, it's not the total current, but the current this side is going to be equal to the PD, that is V over resistance. A PD of 2 volts implies that the current across this part, this 2 ohm resistor, 2R resistor is going to be 1 over R in amperes. So the current this side is 1 over R in amperes. So that means the PD across 3R is going to be equal to, I'm using Ohm's law, V is equal to IR. Remember, the current is the same. The current here is going to be 1 over R. So PD across 3R is going to be current times the resistance. The current we have set is 1 over R, and the resistance is 3R. So it means the PD across that one is going to be 3 volts. Similarly, the PD across the other one is going to be 1 volt. So this is 2 volts, 1 volt, 3 volts, giving us a total PD of it is giving us a total PD of 3 plus 2 plus 1, which is 6 volts. So the PD across this block here is going to be 6 volts. So the question is, what is the EMF of the battery? Of course, the EMF is going to be 6 volts. Because the PD across the other block, or the PD across these points, is the sum of the PDs across all these resistors, which we have got as 1 volt plus 2 volts plus 3, which is 6. So the EMF of the battery is going to be 6 volts, because a combination of all those 3 resistors gives something which is in parallel with 4R, which is also in parallel with the cell. So the EMF is 6. Note how I've got 6 volts. I've said 3 volts across 3 ohms plus 2 volts across 2R plus 1 volt across 1R. The current in a component is reduced uniformly. Okay, that means I can do a graph, which is a straight line, because the current is reduced uniformly. So if I sketch a graph, so this is going to be a straight line starting from 100. This is a graph of current against time. So it is from 100 up to this is 20. Remember, this is in millivolts. 100, milliamperes, 20 milliamperes. It reaches 20 milliamperes in a time of 8 seconds. So this is 0. Let that also be 0. So what is the charge that flows through during this time? So the average charge here, we shall find the area under the graph, and you see that is a trapezium. Although charge is supposed to be current times time, from this graph here, since the current is not constant, we shall take the area under the graph. So charge is going to be equal to the area under this graph, which is actually trapezium. You see that this is a trapezium, so it will be a half. A trapezium is a half A plus B, so this will be A, the other side will be B, and this will be H. For those who do mathematics, the area of a trapezium, this will be A will be 20, millimeters, milliamperes, and B will be that is 0 to 100. Then what is going to act like my height is going to be 8. So this is going to be equal to 20 plus 100 times 8 divided by 2. So this is giving me a 480 millicolumns. So it is 480 millicolumns. So we cannot just subtract 100 minus 20 then multiply by time to find the current, because the current is reducing linearly. So what is very important is the average current here, where the average current is going to be 100 plus 20 divided by 2, which is the same as that. And this gives you 120 over 2, which is 60 milliamperes. That means a charge can now be I times T, which average current is 60 milliamperes, then times 2, which is 8. And I think 60, 8 times 60 gives you 480. So it is 480 millicoulombs. So it is milliampere converted from milliamperes. That's why I'm getting it direct. Okay, an electric current is passed from a thick copper wire through a section of thinner copper wire before entering a second thick copper wire as shown. Which statement about the current and the speed of the electrons in the wires is correct? So let's first look at the expression which relates current to the speed. We know that current is equal to never. Note that in these wires, the current is constant, N and E are constant, so it is only V which is varying with cross-sectional area. And since they are on the same side of the equation, V is inversely proportional to the cross-sectional area. What does that mean? If the wire is thicker, it has a greater cross-sectional area, therefore the diffusive velocity of the particle is going to be smaller. So let's check the alternatives. The current and the speed of the electrons in the thinner wire are both less than in a thicker wire. The current is the same. The current and the speed of the electrons in this is the same in all the wires. The current is the same, but the speed is not the same because speed is inversely proportional to cross-sectional area. The current is the same in all the wires, which is true, but the speed of the electrons in the thinner wire is greater. The thinner wire has a smaller cross-sectional area, therefore the speed is going to be greater. So the answer is going to be C. An electrical device of fixed resistance 20 ohms is connected in a series with a variable resistor and a battery of e.m.f 16 volts and a negligible internal resistance. What is the resistance of the variable resistor when the power dissipated in the electrical device is 4 watts? I think this is a repeated question. At this point, you must have noted that now many questions are being repeated. That's why I guarantee that the more you practice these questions, the more you can pass them in the exam. And by the way, when you're preparing for AS, it is better to practice with the multiple choice questions rather than structured questions many times, because multiple choice give a good insight into what you are supposed to arrive at every time. Okay, so since we have the power through this device, let's find the current through it. From power is equal to I times V, it means the current through it is power over V. The power is 4. The power is 4, and no, let me use I squared times R. Power is I squared times R, meaning I is going to be power divided by R, and this will be under the square root. So this will be square root of 4 divided by 20. Square root of 4 divided by 20, root of 4 divided by 20. So that is approximately 0.45. So I'll write 0.45 amperes. That is the current. I want you to know that it is the same current through the variable resistor. What is the resistance of the variable resistor when the power dissipated in the electrical device is 4 watts? So the resistance here is R. Let's find the current through it is going to be 0.45. So we can now find that resistance. Since I know the current, I know that current through the circuit is equal to the EMF divided by total resistance. So the current is 0.45 is equal to the EMF, which is 16. Total resistance is going to be 20 plus resistance of the plus the resistance of the device. I mean plus the resistance of the variable resistor. So we just cross multiply. We shall have 0.4 times 20, 0.45 times 20, which is 9, plus 0.45R is equal to 16. So we collect like terms, 16 minus 9, and we divide this by 0.45, which gives us 15.5 recurring, which is approximately 16. So R is approximately 16 ohms. So the answer is going to be A. A copper wire is cylindrical and has resistance R. What will be the resistance of a copper wire of twice the length and twice the radius? Twice length, twice the radius, twice the length and twice the radius. Okay, so we know that for a wire, resistance C is equal to rho L over cross-sectional area. They have given us radius. So this time I'll just restrict myself to radius. So it means, where should I work? Okay, let me use this part here. So for the first wire, resistance R is going to be equal to resistivity. Both of them are copper wires. A copper wire is cylindrical and has that resistance. What will be the resistance of a copper wire of twice? So they both are copper. Resistivity is the same. For the first wire, let's say its length is L, and its area is going to be pi times R squared. For the second wire, its resistance R2, I'll put R2 is going to be rho. Its length is twice L divided by its radius. Its radius is twice R, so it is pi times twice R, but this is squared. When you simplify this, you get 2 rho L divided by, when I square this bracket, I get 4R squared, so the 4 is out. I'll pull out the 4. Then I remain with the pi R squared. Remember, this part here is the same as that part there, so this is 2 over 4 times R, which is a half R. So this gives us a half R. So the new resistance is a half of the first resistance, making the answer to be B. The diagram shows the electric motor for a garden pump connected to a 24 volts power supply by an insulated 2-core cable. The motor does not work, so to find a fault, the negative terminal of a voltmeter is connected to the negative terminal of the power supply, and its other end is connected in turn to the terminals X and Y at the motor. So they are saying the negative terminal of the power supply and its other end is connected in turn to terminals X and Y. The motor does not work. So to find the fault, the negative terminal of a voltmeter is connected to the negative terminal of the power supply, as we see here, and its other end is connected in turn to terminals X and Y at the motor. Before seeing the questions, let us assume this is connected to terminal X. If it is connected to terminal X, it means the PD across here, X is of course is going to be 24. Why? This one is at 24 volts, this one is at 0, so the PD across X is going to be 24. And let's check the table. The table shows that X is always 24 for whatever connection. The voltmeter reading when connected to X, it is always 24. So X is always 24. So if the PD is 24 at X, it means there is no fault in X. There will be no fault before X on the other side. So that means we cannot have a fault on the positive cable. So this is the positive wire, this is going to be the negative wire. If the PD across X is always 24 throughout all the options which have been given, it means there is no fault on the positive, there is no fault on the positive cable, the positive wire of the cable. So there is no fault on the positive wire of the cable. So this conclusion that break in the positive wire of the cable, that one, it means it is wrong. If there is a break in the positive wire of the cable, then the PD, the reading of the voltmeter when connected to X cannot be 24. So there is no break in the positive wire of the cable if X is always 24. Then number 2, let's think of a situation if there was a break in the lamp, I mean in the pump. If there was a break in the pump, let us assume there is a break in the pump or there's a problem with the pump. This takes long to load, I don't know why. If there is a break in the pump, if there is a break in the pump, that means if there is a break in the pump, X would be at 24 volts. Remember there is a break in the pump. So that means current does not reach Y. So it means Y would be at 0. If there is a break in the pump, X will be at 24, therefore Y will be at 0 because current is not continuing after the pump. Therefore it means because current, it means this other cable is actually cut out. So if there is a break in the pump, X will be at 24, but Y would be at 0. So what does this imply? Let's check. If there's a break in the pump, X will be at 24 and Y would be at 0. Let's check here. Where there is a break in the pump, okay, break in connection within the motor, Y would be at 0. Here they're showing Y is at 24. It can't be at 24, yet current is not moving through it. Yet current is not moving through the motor. So this one is also out. So we have eliminated A and C. Okay, let's go back. Suppose there is a break in the negative wire. Let's assume there is a break in the negative wire. Remember I said the upper wire is positive, the lower wire is negative. If there is a break in the negative wire, when I put the voltmeter at X, it will read 24. Even when I put it at Y, it will still read 24, even though the current is not continuing on its way the other side. So if I put the voltmeter across Y, because current is continuing from X to Y, even though it is not going back to the negative terminal via this negative wire, the potential at Y is supposed to be 24. So if there was a break in the negative wire, X will be at 24 and Y should also be at 24. So let's check that. If there is a break in the negative wire, X is at 24, should be at 24, and Y should also be at 24. What is the implication of this? Break in the negative wire, X should be at 24 and Y should also be at 24. So this one is also eliminated. So B is out, meaning the answer is going to be D. Let's try to evaluate this. If there is a break in the negative wire of the cable, X is already at 24. The potential at X is at 24, but the current is going to go through the motor because there is no break in the motor. So if current goes through the motor, it reaches point Y, it means point Y will also be at 24 volts. It will be at the same potential as X. So even though there is a break in the negative wire, current is not continuing through the negative wire. So it means if I bring the voltmeter at Y, it will read 24. In other words, it will be like a series. This is a positive. Here we have a positive cable of the wire. Somewhere here we have X, we have the motor, and we have Y somewhere here. And this is going to be continuing to the voltmeter, and again going back to the negative terminal here. So if we bring the voltmeter at Y, remember the negative part of the wire has been broken, so it is equivalent to not putting it there. So it means the potential here is 24, the potential will be 24, the potential will be 24. So the potential will be 24, and this will be of course 0. So our answer is going to be precisely D. Okay, so when y is at when we connect at x, the voltmeter reads 24. When you connect at y, the voltmeter reads 24. Then we can conclude that there is a break in the negative y of the cable. I mentioned if there was a break in the positive y of the cable, x could not be at 24. It could be at 0 because current would not be reaching even x. Okay. In the circuit shown, the resistance of the thermistor decreases as temperature increases. Resistance decreases as temperature increases. That means, remember, V is equal to IR, or you can look at the potential divider. So the PD across the thermistor must have decreased. And if PD across the thermistor decreases, it means V here across PQ must increase because the total should be equal to the PD of the supply. So which graph shows the variation with Celsius temperature theta of the potential difference V between points P and Q? First of all, we have seen that it actually increases. It actually increases. So the A is a decrease, B is a decrease. Those ones are out. But this variation is not linear because we get it from the potential divider formula. That is V out is going to be the PD across PQ, which is going to be the resistance there, over R of the thermistor plus R, which is here, let this be R, and let this be R of the thermistor. So it is going to be R over R of the thermistor plus R, then times the voltage supply of V in. Remember, we have just said that if the PD across the thermistor decreases, it means the PD across R increases. But note, for the PD across R to increase, it means, of course, R, this one is fixed, this one is fixed, and the R of the thermistor is the one which is decreasing. And this decrease can never be linear, which means this is going to be 0. I mean, this is going to be wrong, so our answer is going to be this. So if you look at a graph of course, as temperature increases, it means the resistance of the thermistor decreases. Therefore, the PD across the fixed resistor increases, but because the decrease is not linear, it means also the PD across the fixed resistor will not increase linearly. Therefore, D is wrong. A 20 volts DC supply is connected to a circuit consisting of 5 resistors L, M, N, P, and Q. If you have been following very well, this is a repeated equation. We have done it almost more than 2 times earlier on. So if this is 20 volts, remember this resistor here is neither in series nor in parallel. So the PD across P plus the PD across Q should be 20. The PD across L plus the PD across M up to this point should also be 20. That means I can now tell what M is. So M is going to be 20 minus 7, which is going to be 13. I can tell what P is. When I get this, the PD across P and the PD across L, and I subtract them, I should be able to get 4, which is the potential difference across these 2 points. So it means that the PD across P, which I'm calling P, minus the PD across L should give me 4 volts. So it means P is going to be equal to 4 plus L, which L is 7. That gives me 11. Then the PD across Q can be got from, remember this is, if this is 11, so it means Q is going to be simply 20 minus 11, which gives us 9. Or you can get Q via M and N. So Q can be M minus N, which gives us still 9. Therefore, note that M should be 13 volts, P should be 11 volts, and the Q should be 9 volts. So let's check for such alternatives. Okay, we say the M should be 13, so this is wrong, this is wrong, we have these two. And we say the P should be 11, so this is correct, this is wrong, this is wrong, this is wrong. And we say that Q should be 9, so our answer is going to be C. There is a current of 10, I hope this is 10 There is a current of 10 milliamperes in a conductor for half. This is for half an hour. How much charge passes a point in the conductor in this time? You and me note that charge is equal to current times time. The current is 10 times 10 power negative 3, then times the time, which is half an hour, that is half, times 3600. So this is 10 exponent negative 3 times half is 0.5 times 3600, which is 18. So the charge is equal to 18 coulombs. So our answer is C. An iron wire has length 80 meters and diameter 0.5 millimeters. The wire has resistance R. A second wire has length 2 meters and diameter 1 millimeter. What is the resistance of the second wire? Okay. What is the resistance of the second wire? Okay, let's use resistivity. Let's use resistance is equal to rho L over cross-sectional area. They have given us a diameter, so it becomes, okay, area. So this becomes 4 rho L over pi d squared, because area is pi d squared over 4. So let this be for the first wire. An iron wire has that length. They have given us length and its diameter. The second iron wire resistivity is the same. They have given us L. They have given us the diameter. So I will just substitute the values here. Okay, let me substitute the values here. This will be equal to 4 times resistivity rho times the length, which is 8, divided by pi. The diameter has been given as 0.5 squared. I will not convert the units for diameter because I know I'm going to divide these equations. Then for the second wire, I will call it R2. This will be 4 rho. The length of the second wire is 2 meters, so this is times 2 divided by pi. Then times the diameter is 1 millimeter. I'll just say 1 squared. That is 1 squared. So I just combine these two equations. I'll just combine these two equations, maybe by simple division. I will divide R2 by R. So R2 divided by R, this is going to be 4 rho times 2 divided by pi. Of course, this 1 squared is useless, so that I'll just say divide by pi. Okay, maybe times 1 squared, no problem. Then times, I get the reciprocal. Pi times 0.5 squared divided by 4 rho times 8. I'll change the color so that I cancel out some things. So pi is out, 4 is out, rho is out. So I am remaining with 2 times 2 times 0.5 squared, which is 0.5. So that is 0.5 divided by, so 0.5 divided by 8 in the denominator. So that is divided by 8, which gives me 16. So this is giving me 16. So it means R2 is going to be 16 times R. So our answer is going to be A. R2 is going to be 16 times R, so the answer is going to be A. In the circuit below, the ammeter reading is I and the voltmeter reading is V. When the switch is closed, which row describes what happens to I and V? Which row describes what happens to I and V? Okay. When the switch is closed, so when the switch is closed, there will be a short circuit here, so current will not go that side. Current will take this route, so the PD across here will be 0. The PD across here will go to 0 because current takes this route. So since current takes this route, the resistance has actually decreased. It means the current flowing increases. So the current increases, so we eliminate A and D. But note that the PD, since current is not going through that route, it takes the least resistive path possible. When the switch is closed here, current takes this route, this will be almost out. The PD across this will be 0. So it means the voltmeter reading decreases and it goes to 0. So our answer is going to be B. V decreases, it goes to 0. Reason, when we close the switch, current will dodge that resistor. Of course, it can't dodge this one because it is in series with the battery. But it can dodge this one because there will be short circuit here. It will take the least resistive direction. Okay. A potential divider consists of a light-dependent resistor in series with a variable resistor of resistance R. The resistance of the LDR decreases when the light level increases. The variable resistor can be set at either high resistance or low resistance. Which situation gives the largest output voltage? So output is against a variable resistor. So it means this resistor here should be higher. So R should be greater. If we want a large output, because V out is going to be R over R plus the resistance of the LDR, then times V in, which is equal to 10 times 10. So R should be greater. And if R should be greater, then the resistance of the LDR should be smaller. How do we make the resistance of the LDR to be smaller? Then the light intensity should be higher. So the light intensity should be higher if we want the resistance of the LDR to be smaller. Therefore, let's see which situation gives the largest output voltage. We have already seen R should be high. R should be high. So R should be high. So we eliminate low. Then the light intensity should be high so that the resistance of the LDR is low. So this should also be high. So our answer is going to be A. Light intensity should be high, or the light level should be high so that the resistance of the LDR is low, so that the PD across the LDR is small, making the PD across the fixed resistor to be high. So our answer is going to be A. The circuit below has a current I in the resistor R. What must be known in order to determine a value of I? What must be known in order to determine the value of I? Of course, it is easy to tell I if I know this as 4. So 4 is going to be 3 plus I. This is, I'm using Kirchhoff's first law at the junction. The sum of current entering the junction should be equal to the sum of current leaving the junction. So it means I would even be 4 minus 3, which is 1 ampere. So what must be known? Let's see the alternatives. e.m.f of the power supply, resistance of S, Kirchhoff's first law. Kirchhoff's first law is enough for us to be able to tell what I is. So when will one coulomb of charge pass a point in an electric circuit? When will one coulomb of charge pass a point in an electric circuit? One coulomb of charge. Remember, charge is equal to current times time. So let's check. 1 ampere moves through a potential difference of 1 volt. Current and PD, current and PD, that does not give us 1 coulomb. When a power of 1 watt is used for 1 second, power of 1 watt is used for 1 second, that is, I think, energy, not charge. When the current of 5 milliamperes, when the current is 5 milliamperes for 200 seconds, let's check that one. Current is 5 times 10 power negative 3, then times 200. So we have 5 exponent negative 3 times 200, which is 1. So the answer is going to be C, because this gives us 1. So our answer is C. Two copper wires of the same length but different diameters carry the same current. Which statement about the flow of charged particles through the wires is correct? Two copper wires of the same length but different diameters carry the same current. Which statement about the flow of charged particles through the wires is correct? So current is equal to never. They carry the same current. They have the same length. We also note that resistance. We also note that resistance is equal to rho L over cross-section area. So let's see the alternatives which are there. Charged particles are provided by the power supply. Therefore, the speed at which they travel depends only on the voltage of the supply. Charged particles are already there in the metal conductor. The charged particles in both wires move with the same average speed because the current in both wires is the same. But they have different diameters, so they have different areas. Therefore, and we see that V is inversely proportional to cross-sectional area. So this one is also not correct. The charged particles move faster through the wire with a larger diameter because there is a greater volume through which to flow. A greater diameter means a greater area, which means a smaller drift velocity. Therefore, this one is not going to be correct. The charged particles move faster through a wire with a smaller diameter because it has a larger potential difference applied to it. So the wire with a smaller diameter, of course, has a higher resistance. Therefore, the P is higher. So the answer is going to be D. Even you can see drift velocity is inversely proportional to cross-sectional area. Smaller area means a higher drift velocity. A power cable X has resistance R and carries a current I. A second cable Y has resistance 2R and current I half I. What is the ratio? Power dissipated in Y over power dissipated in X. Okay, so we know that power is equal to I squared times R. So for Y, the power is going to be for Y, the power is going to be I a half I, but squared. Then times the resistance, which is twice R. Then for X, the power is going to be I times R, I squared times R. So R cancels out. So this is going to give us a quarter I squared times 2 divided by I squared, which is a quarter times 2, which gives us 1 over 2. So our answer here is going to be B. The diagram shows a circuit with 4 voltmeter readings V, V1, V2, and V3 as shown here. Which equation relating the voltmeter readings must be true? Before we see the available options, let's see some of the possible equations. Now you will notice that V2 is giving a PD across R. It is also giving the PD across to R. That means the V2 and the V3 are the same because are giving the same reading because they are connected across the parallel combination. So V2 and V3 are the same. So you notice that actually V is the total EMF. So V should be equal to PD outside, which is V1 here, the potential drop there, plus V2, which is here. Or V can also be V1 plus V3. After all, V2 and V3 are the same. So let's see the options which are there. So V is also V1 plus V3. So let's see the options which are there. Which equation relating the voltmeter readings must be true? Which equation relating the voltmeter readings must be true? Let's see the voltmeter readings. So we have this one. This one is not true. We cannot add the PDs which are in parallel. This one is showing V is equal to V2 plus V3. We cannot add these ones. V3 is equal to twice V2. That is not true. I think this is the most appropriate equation because we had that V was equal to V1 plus V3, which means V minus V1 can be equal to V3. I think that makes sense. V minus V1 is equal to V3. I think we have seen that. The PD V3 here, when I add it to V1, I can get V. So that is V minus V1 is equal to V3. A light dependent resistor is connected in series with a resistor R and a battery. The resistance of the LDR is equal to the resistance of R when no light falls on the LDR. When the light intensity falling on the LDR increases, that is obvious, the resistance of the LDR is going to decrease, which means the PD across the LDR is also going to decrease. Therefore, the PD across here, because this is constant, the PD across here, it must increase because the sum should be equal to EMF. So which statement is correct? The current in the L in R decreases, it actually increases. The current in the LDR decreases, it actually increases because the total resistance becomes smaller. The PD across R decreases. The PD across R actually increases. The PD across the LDR decreases. That is very true. The PD across the LDR decreases. The PD across R is supposed to increase. So V across R becomes bigger. The diagram shows the circuit for a signal to display a green or a red light. It is controlled by the switch S. The signal is somewhere from S to which it is connected by a cable with a green, red, and black. At the signal, the green and red wires are connected to the corresponding lamp, and the black wire is connected to a terminal X to provide a common return. The arrangement is shown correctly connected and with the switch set to illuminate the red lamp. So the switch is set to make the red lamp to light. Okay. During maintenance, the wires at the signal are disconnected, and when reconnected, the black wire is connected in error to the green lamp. So black is connected to the green lamp instead of terminal X. The red wire is connected correctly to its lamp, and connections at S remain as in the diagram. So this is what has been shown. During maintenance, reconnection is done in this way. So we see the black wire which was here has been removed and has been taken here. So you will notice that now this red is in series with the green. Therefore, both of them are going to light. However, the PD of 12 volts is going to be divided into red and green. Yet before, the PD of 12 lights would either all of it be across red, but not across green, or all of it across green, but not at red. Now that is being divided into 12 volts is being divided into the PD across red and the PD across green. First of all, both of them will light, but they will be dimmer because the PD across them is smaller. Both of them will light because there is current going through both of them. They are now in series, but they will not light normally because the PD of 12 volts is being divided into them. So when the system is tested with the switch connection to the red wire, what does the signal show? The green lamp illuminated normally, not at all, because the PD across it is less than 12. The red lamp illuminated normally, not at all, the PD across it is going to be less than 12. The red and green lamps both illuminated normally, that is not true. They all illuminated, but the PD across them was smaller. The red and green lamps both illuminated dimly. The answer is going to be D. They are going to be dim because the PD across them is going to be smaller since they are now in series. 4 identical resistors are connected in the three networks shown below. Which arrangement has the highest total resistance and which has the lowest? When I look around, this one should be having 3 should be having the highest and 1 should be having the lowest. Let's check. If they are identical, let's say this is R, 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 R. So this will be 3R and this is R. 3R is in parallel with R, so that gives us 3R times R over 3R plus R. Resistors in parallel is product over sum. And I think this gives us 3R divided by 4. Let's check this one. These are in parallel, so this is R plus R and R. When they are in parallel, they give us a half R. So this is a half R. A half R we add it to R. A half R we add to R in the upper loop. In the upper branch, we have R plus a half R, which is 3 over 2 R. So 3 over 2 R is in parallel with the R at the bottom. So you have 3 over 2 R times R divided by 3 over 2 R plus R. That is product over sum. And I think this gives you 3R over 2, I think that is 5, 3R over 5. So that is 3R over 5. You can simplify that and see. That is 3R squared over 2. This in the denominator you have 5R, so some people may not see that. So let's say this one becomes 3R squared over 2 divided by LCM here is 2, so that is 5R over 2. So that is 5R over 2. So the 2 cancels, you remain with the 1R cancels, you remain with 3R over 5, which is there. Let's check the first one here. These two are in parallel. I mean in series, they give us a total of 2R. Then this is R, this is R. So we have 3 resistors in parallel now. So total resistance is going to be got from 1 over R plus 1 over 2R plus 1 over R. This is 1 over total. LCM here is 2R. 2R divided by R, that is 2 plus 1 plus 2, which gives me 5 over 2R. Then I get the reciprocal. R total is going to be 2 over 5R. I think 2 over 5 is the smallest. You can check with the calculator. And I think 3 over R is the largest. 3 over R is 0.75. I mean 3 over 4. 3 divided by 4, 0.75. Then 3 divided by 5, that is 0.6. Then the other one is 2 divided by 5. 2 divided by 5, that is 0.4. So the smallest is 1. So our answer is going to be C. Which values of current and resistance will produce a rate of energy transfer of 16 joules per second? 16 joules per second, rate of energy transfer, I think that is power. So power is equal to I squared times R. The power should be 16 joules per second. That is 16 is going to be equal to I squared times R. So let's do what we call inspection. We check which pair gives us 16. I'll start with the first one is obviously wrong. 1 squared times 4 cannot be 16. 2 squared is 4 times 8 is not 16. That is 34. 4 squared is 16 times 1, that is 16. So the answer is going to be C. A copper wire is stretched so that its diameter is reduced from 1 millimeter to a uniform 0.5 millimeters. It is stretched. The resistance of the unstretched copper wire is 0.2. What will be the resistance of the stretched wire? Now, they have not given us anything to do with resistivity. They have not given us anything to do with the length, but they have told us to stretch. If a wire stretches, it means length increases, cross-sectional area decreases, the volume remains the same. So let's try to use inspection and find the volume of the new wire. Volume is cross-sectional area times length. Volume will be cross-sectional area times length. Remember, without forgetting, that area is going to be pi d squared. Area is going to be pi d squared divided by 4, since they mentioned diameter. But before we go there, let the first wire have area A, and the length of the first wire, let it be L. let the second wire have area A2 and the length of the second wire is going to be L2. Okay, so it means you will notice that the length of the second wire L2 is going to be equal to A over area 2 times the original length. But remember, area is pi d squared over 4, so I'm going to substitute. So the length L2 is going to be equal to A to be pi, its diameter is the first wire, remember, its diameter is 1. I will not convert the units, I will just say 1. 1 squared divide by 4. Then divide by A2. A2 is equal to is going to be pi. So I'm going to get the reciprocal. So 4 goes up. So it will be 4 divided by pi. Where there is diameter, I'm going to put there 0.5 squared. I will not change the units because I'm going to divide. Then times this L here. So I wanted you to see that pi cancels, 4 cancels. And if those ones cancel, pi cancels, 4 cancels, you remain with 1 over 0.5 squared, which is 4. I guess 1 over 0.5 squared is 4. 1 divided by 0.5 squared, that is 4. So L2 is going to be 4L. L2 is going to be 4 times L. So the length of the new wire is going to be 4 times the original length. Now let's find the resistance. Resistance of the first wire is going to be 4 rho L over diameter over pi d squared for the first wire. For the second wire, okay, I will not put in okay, I can even put in values, no problem. But I noticed that this diameter here is half the other one, so I can put in half, no problem. For the second wire, the resistance R2 is going to be 4 times rho. Where there is length for the second wire, I'll put there 4L, so this is times 4L. Divide by pi, where there is diameter, this is a half of the other one. So I'll put there a half. So this will be a half of d but squared. And this simplifies to 4 into brackets 4 rho L divided by here there is a half squared which is a quarter, so I'll bring a quarter out. I'll pull out a quarter, then in brackets I remain with pi d squared. Note that this quantity here is the same as this one here. So where there is this quantity here, I'll just put there R. Therefore, this means that R2 is going to be 4 divided by a quarter, I think it is 16. So this will be 16 times R, where R was 0.2. The initial the unstretched copper resistance was 0.2. So this is going to be 16 times 0.2, which gives us, I think, 3.2. 16 times 0.2, that is 3.2. So this gives us 3.2 ohms. This is quite technical, but when you have experience, it becomes easy. So our answer is 3.2 ohms, which is D. 4 statements about a potential difference or e.m.f. are listed. Number 1, it involves changing electrical energy into other forms, that is PD. It involves changing other forms into electrical energy, I think that is e.m.f. It is the energy per unit charge to move a charge right round a circuit. The energy to move a charge right round the circuit is e.m.f. And the work done per unit charge by the charge moving. So the work done by the charge moving, that is PD. So which statements apply to potential difference and which apply to e.m.f? So we have already seen them. 1 and 4 is PD. 1 and 4 is PD. 2 and 3 is e.m.f. So our answer is going to be B. The diagram shows a 4-terminal box connected to a battery and 2 ammeters. I think we have done this question earlier on. The currents in the 2 meters are identical. So the current here is the same as the current here. So one, we are going to choose which circuit within the box will give this raise. So of course, this one is going to be out. Why? When I put it here, the circuit will remain open. So there will be no current the other side. So that one is already out. Then I will also ignore this one because there will be no current going through the resistor this side. So there will be a short circuit there. So that one is out. I will also ignore this one because at this junction there will be current taking this path and current will take that path. That means current will divide. The current will divide. It will not be the same when it reaches this junction here at 1. So this is out. That means the answer is going to be D. So it means this part here can just be joined, and this part here we shall put the load here. So that means the current here is the same as the current there. In the circuit below, P is a potentiometer of total resistance 10 ohms. Q is a fixed resistor of resistance 10 ohms. The battery has EMF 4 volts and negligible internal resistance. The voltmeter has a high resistance. That means no current flows through the voltmeter. The slider on the potentiometer is moved from X to Y. And the graph of voltmeter reading V is plotted against the slider position. Of course, when we take it to X, the reading must be 4 volts because it gets the PD across P plus the PD across Q. When we take it to Y, the reading must be, because Q is 10, the reading must be 10 divided by total resistance, which is 20 times 4, which gives us 2 volts. So at Y, the voltmeter should read 2 volts, and at X, it should read total PD across P plus Q. I'm saying at X, it reads PD across P plus PD across Q, which is the EMF, and that is 4 volts. At Y, it gives the PD across Q alone, which is the resistance of Q, that is 10, over total resistance, which is 10 plus 10, then times the voltage supply. That is the potential divider formula, that is at Y. So our graph should be, so this one is showing at X it is 0, that is not true. At X, it is 4. So our graph should start from 4. So this one is also wrong. At X it is 4, but at Y it is 2. This one shows that at Y it goes to 0, yet it goes to 2. So our answer is going to be B. The diagram shows a resistor network. The potential difference across the network is V naught. Is V. The diagram shows a resistor network. The potential difference across the network is V. Is the equation shown below correct for the network? Okay, let's see the network. So that is the network. And the equation which is given is V is equal to current into 1 over R1 plus 1 over R2 plus R3. This one is not total resistance. That one cannot be total resistance because the two are in parallel, but then we get the reciprocal. The correct equation would be V equals to I into, for the parallel combination, to be product R1 plus times R2 over the sum R1 plus R2. That's total resistance here. Then maybe plus R3. That would be the correct equation. But this one does not lead to that. So when you see yes, that is wrong because the equation is not correct. No, because it should be I divided by 1 over R1 plus 1 over R2 plus R3. I divided by instead of multiplication, so that is still wrong. And if I say I divide by this, it is still wrong. It doesn't give me this equation here. So the answer is going to be D. No, because the term 1 over R2 and R3 have different units and cannot be added. They have different units, or they have different amounts, so they cannot be added. They have different units and therefore they cannot be added. In fact, for If 1 over R is per ohm, yet R is ohm. R3 is ohm, so you can't add 1 over R2 plus R3. 1 over R3 will be per ohm, and R3 is ohms, so you can't add those two quantities. However, if you do the product, this one is going to be ohms squared divided by ohms in the denominator, which gives us ohms again, plus ohms. It can be added. Nucleus X is at the start of the sequence, and after the decays have occurred, nucleus Y is formed. This is particle physics, and something was left out of this equation. The equation was left out, so I will not answer this equation here because the equation was left out, but nevertheless, we must have answered it in particle physics or atomic physics. The potential difference between points X and point Y in a circuit is 20 volts. The time taken for charge carriers to move from X to Y is 15 seconds. In this time, the energy of the charge carriers is 12 volts. Oh, what a beautiful, simple question. We know that energy is equal to power times time, which is IV times T. They have given us the energy as 12 joules. So we shall say 12 is equal to I, which is I is not known, then times V, which is 20, then times T, which is 15. So we just press our calculator and find I. I will be 12 divided by 20 times 15, which gives us 0.04. So I is 0.04 amperes. So our answer is going to be A. Why can't I change the color? Some people are colorblind. In a fire alarm system, a thermistor T has a resistance 2000 ohms at room temperature. Its resistance decreases as the temperature increases. The alarm is triggered when the potential difference between X and Y reaches 4.5 volts. What is the resistance of the thermistor when the alarm is triggered? I think this is also a repeated question. So I will say resistance of the thermistor is T. The PD across 150 ohms is 4.5. So we know that, remember, using the potential divider formula, V out is equal to the resistance across, let's say, XY, divided by resistance XY plus T, that is total resistance, then times the voltage supply, which is 12. So V out is 4.5 across XY, should be equal to XY, which is 150, divided by 150 times plus T. Then I will multiply this by 12. So we just press our calculator. 150 plus T is equal to, I'll just say 150 times 12. Then I divide this by 4.5. So on one side I have 150 plus T, the other side I have 400. So we just subtract 400 minus 150, which gives us T as 250 ohms. A network of electrical components is connected across a battery of negligible internal resistance as shown in the figure here. The resistance of the variable resistor is increased. So resistance of this one is increased. If the resistance here is increased, it means the PD across here goes up, the PD here goes down. The PD across here goes up, the PD across here goes down. However, if we use Kirchhoff's laws anyway, the PD across this point here must be going down. So the voltmeter reading must decrease. So we can eliminate this one, we eliminate this one. So A and D are out. When the resistance of the thermistor increases, of the variable resistor increases, the PD across it increases. So V here goes up, which means V here goes down because the PD across these two terminals must be the EMF. However, the PD across the fixed resistor has not changed because the PD across the fixed resistor is again the PD between these 2 points. And from current equals to V over R. The fixed resistor is not changing and the PD across it is not changing. It means the current will not change. So the current here is not changing because the PD across the fixed resistor is still the same as the EMF E. The PD across these 2 points is the PD across the fixed resistor, which is the same as the EMF E. So it means the current through the ammeter will not change. So the answer is going to be C. The diagram shows a potentiometer circuit. Okay. The diagram shows a potentiometer circuit. The contact T is placed on the wire and moved along the wire until the galvanometer reads 0. Remember the EMF, when the galvanometer reads 0, the EMF across cell 2 is the same as the PD across XT. That is when there is balance because PD is directly proportional to the length. In order to calculate the potentiometer, the potential difference per unit length, that is PD per centimeter of the wire XY, which value must also be known. So to find the potential difference, a PD per centimeter per unit length of the wire XY, then of course we need to know E2 because E2 is going to be that the PD across XTY, which is the same as the PD per unit length, then times length L. So our answer is going to be the EMF E2 because the PD across the wire when there is balance is the same as the EMF of that cell. So if I know the PD across XT, then I can get the PD per length. Then I can use that PD per length for other purposes. So that is the purpose of a potentiometer, to compare PDs or to compare EMFs. The graph shows the variation with the length L of a resistance R for 2 wires X and Y made from the same material. Same material means same resistivity. So resistivity of X is twice resistivity of Y. That is automatically wrong because they are from the same material, they have the same resistivity. Cross-sectional area of X is equal to twice cross-sectional area of Y. Let's check this out. Resistance is equal to rho L over cross-sectional area. You notice that resistance is inversely proportional to cross-sectional area. Now we are seeing resistance of X is greater than resistance of Y, and yet resistance is inversely proportional to cross-sectional area. The one with the higher resistance should have a smaller cross-sectional area, so that this one is automatically wrong. When equal lengths of X and Y are connected in series to the battery, the power in X is equal to twice the power in Y. We can try to check that. If they're in series, I is the same. The current is the same, and we know that power is equal to I squared. Power is going to be I squared R. The power in X is going to be, the current is the same I squared. The resistance of X, let's use the maximum values. The resistance of X is going to be 20. The power in Y is going to be I squared. The resistance in Y is 10, maximum resistance. So you notice that power of X, or the power in X, is equal to 2 times the power in Y because this is 10, the other one is 20. So this means our answer is going to be automatically be C. I don't need to check D, number 35. A cell of internal resistance 2 ohms and EMF 1.5 volts is connected to a resistor of 3 ohms. What is the power, the PD across the 3 ohm resistor? So let me first find the current here. We know that current is going to be equal to the EMF divided by total resistance. So the current is going to be the EMF, which is 1.5. Total resistance is 2 plus 3, which is 5. So that is the current. Then when I find the PD across the external resistance, I'll get the current through it. Because they're in series, the current is the same. The current is 1.5 divided by 5, that is the current, times the resistance, which is 3. So we can check 1.5 divided by 5 times 3, which gives us 0.9. So the PD uh, across the 3 ohm resistor is going to be 0.9 volts. So our answer is going to be C. The ammeter reading in the circuit below is I. Another circuit containing the same voltage supply, 2 switches, an ammeter, and 2 resistors, each of resistance R, is shown here. Okay. Which row is not correct? Which row is not correct? Which row is not correct? I see these, they are showing S1, S2, and the ammeter reading. Let's try to, before we see the table, let's try to investigate and see. When will there be, remember initially the ammeter reading was I, when it is alone like this. When will the ammeter reading give the same value I, or what will be the reading of the value I when we do a combination of these switches being closed? For example, suppose I close S1. S1, I'll use C for closed. S1 closed. S2, I'll use O for open. What is the current? What is the ammeter reading? S1 is closed. S2 is open. Of course, the ammeter reading is going to be I automatically. Then S1 is, let's say S1 is open, S2 is closed. Of course, these two will be in series. The ammeter reading cannot be I. It cannot be I. Then let's say both of them are closed. S1 is closed, S2 is also closed. When S1 is closed and S2 is closed, it is equivalent to having the first part. If S1 is closed, as long as S1 is closed, no current goes through R. As long as S1 is closed, there's a short circuit, so no current goes through R, it just goes through directly the switch to the other part. So the current will still be I, because this one will be out of the circuit. Even if S2 is closed, no current takes through this route when S1 is also closed. Of course, if both of them are open, S1 is open, S2 is open, there will be no current, so that will be 0. Let's see the options which are there. So the first one, A, is saying S1 is closed and S2 is closed. I'm saying the reading will be I because no current goes through S2. So it's like having one resistor in series with the battery, because there will be short circuit, current takes the less resistive path. So current will go through the switch without going through R, even if S2 is closed. S1 is closed, S2 is open, that is automatically I. It is equivalent to having one resistor. S1 is open, S2 is closed. If S1 is open and S2 is closed, we now have two resistors in series. We now have two resistors in series. Therefore, the current reduces, so it cannot be I. If both of them are open, there will be no current, so that is 0. So which row is not correct? The answer is going to be C. A light-dependent resistor has a resistance of about 1 mega ohm in the dark and about 1 kilo ohm when illuminated, that is under light. It is connected in series with a 5 kilo ohm resistor to a 1.5 volt cell of negligible internal resistance. The light-dependent resistor is illuminated in an otherwise darker room by a flashing light. So the flashing light, there's light on equal time intervals and darkness on equal time intervals from the flashing light. So which graph best shows the variation with the time t of potential difference V across R? So we're going to sketch a graph of V with the time. Let's first find when it is in dark, the resistance is 1 mega ohms. So let's see the PD. The PD in darkness is going to be the resistance in darkness, which is 1 times 10 power 6, divided by total resistance, which is 1, that is 10 power 6 plus 5 kilo ohms, which is 5,000, then times the voltage supply, which is 1.5. I think this gives us approximately 1.5 volts. So when it is in darkness, it is approximately 1.5. We can check. 1 exponent 6 divided by 5,000 plus 1 exponent 6. So this is approximately 0.99995 times 1.5 times 1.5. It is approximately 1.5. So our graph should be starting at should have a maximum of close to 1.5 or approximately 1.5. So this one is wrong. This one is also showing. Okay, we can first leave this one. Then when it is in illuminated, the V is going to be 1 kilo ohm. The resistance is 1 kilo ohm. So that is 1 times 10 power 3 divided by total resistance will be 1 kilo ohm plus 5 kilo ohms, which is 6 kilo ohms. So that is 6,000. Then times 1.5. So we have 1,000 divided by 6,000 times 1.5. So this is approximately 0.25. So it goes to close to 0.25. So this one is automatically wrong. And this one is showing that it starts from a value less than close to 0, yet it should be starting with a value in bright light. In darkness it should be having a value very close or approximately 1.5. So our answer is going to be B. And notice if I divide this by 2, I get 0.75. When I divide again by 2, I get around 0.35, 0.325. So it means this is approximately 0.25. So our answer is going to be the minimum is 0.25, the maximum is close to 1.5. A copper wire of cross-sectional area 2 millimeters squared carries a current of 10 amperes. How many electrons pass through a given cross-section of the wire in 1 second? Okay, we want the number of electrons. So we know that charge is going to be equal to the number of electrons times the charge of each electron, but this is current times time. So number of electrons is going to be the current, which is 10 amperes. The time is 1 second divided by the charge of each electron, which is 1.6 times 10 power negative 19. So we have 10 divided by 1.6 exponent negative 19, and that gives us 6.25 times 10 power 19, which makes our answer to be C, 6.3. The battery is marked 9 volts. What does this mean? Each coulomb of charge from the battery supplies 9 joules of electrical energy to the whole circuit, that is e.m.f. So the answer is A. The battery supplies 9 joules to an external circuit for each coulomb of charge, that would be PD. So that is not true. For a battery, 9 volts is e.m.f, which is the energy supplied by a charge through the whole circuit. If it is PD, it is work done when a coulomb supplies a given amount of energy throughout from one point to another point. The graphs show possible IV relationships for a filament lamp and for a semiconductor diode. Of course, without even any analysis, we now know that this is a filament lamp, this is a semiconductor diode. How? For a semiconductor diode, there is a threshold voltage which is about 0.5 or 0.6. It starts conducting after 0.6 volts. That is for a diode. So here it is showing there is a current. When there's no voltage, that is not possible. Okay, we can choose between these two for a filament lamp. We know that I is equal to V over R. And for a filament lamp, it means the gradient here is equal to 1 over R. For a filament lamp, remember temperature with the time temperature increases. And as temperature increases, it means the resistance increases. So if the resistance increases, the gradient must decrease because they're inversely proportional. And the graph which shows the decreasing gradient is going to be P. So for a filament lamp, we have P. For a diode, we have R. So our answer is going to be A. Filament is P, diode is R. The resistance of a metal cube is measured by placing it between two parallel plates as shown in the figure here. The cube has volume V and is made of a material with resistivity ρ. The connections to the cube have negligible resistance. Which expression gives the electrical resistance of the metal cube between X and Y? So we know that resistance is equal to rho L over cross-sectional area. It is a cube, so the volume of the cube is supposed to be equal to L cubed. And remember, the area of the cube is going to be L squared. So it means the resistance is going to be rho times L over L squared, which is going to be equal to rho divided by L, because one L cancels. But note that the volume is L cubed, meaning L is equal to the volume, the cube root of the volume, which is volume power a third. L is going to be volume power a third. So R is going to be rho. Where there is L, I will put a volume power a third. So which expression gives the electrical resistance of the metal cube between X and Y? So the answer is going to be C. The diagram shows part of a current carrying circuit. The ammeter has negligible internal resistance. What is the reading of the ammeter? So we want current here. Okay. So if I say that the current here is I, let me say that the current here is I. Okay, let me say that the current here is I. If the current here is I, remember this is having resistance which is half of this. So the current here is going to be a half of I, because it has twice the resistance, so it should be having half of the current. This 5 ohms is 5 times 1. So it means the current in 5 ohms is going to be 1 over 5 of I. So I can now just sum up these ones, because by Kirchhoff's first law, 5 amperes should be equal to I plus a half I plus a half I, then plus 1 over 5 I. So we shall just add these ones, 1 plus a half, which is 0.5, plus 1 over 5, I think, is 0.2. That gives us, is it 17? Okay. 1 plus, this is a half, which is 0.5, plus 1 divided by 5 is 0.2. So that is 17 over 10I. So this is, it means 17 over 10I is equal to 5. So I is going to be 5 times 10 divided by 17, which is it 2.9? Let me check it again. If the current here is I, because this is twice this is a half I. Am I adding this wrongly? 1 plus 0.5 plus 0.2. Okay, let me start with the bigger value of I. Okay, let me start with the bigger value of I. Maybe it will be easier for us to see this clearly. Okay, if this is I, because this resistor is 5 divided by 2. I mean, this resistor here is 2 point. When I multiply 2 by 2.5, I get 5. So the current here is going to be 2.5 times I. And this resistor is a half of this. So if this resistor is a half of this, or if this current here is I and it is 5 times the other one, and this resistor is 5 times the other one, so this one is going to be, this one is going to be 5I. Okay, I think there is a clear relationship because when I multiply this one by 2, I get 5. When I multiply this one by 5, I get 1. Therefore, I plus 2.5I should be equal to, plus 5I should give us 5 amperes. Okay, so we have 5 plus 1 plus 2.5. I think that is 8.5I. This is equal to 5. So we just divide. We are just going to divide. I is going to be equal to 5 divided by 8.5. Okay, so that is I. That is I. But I want the current through the ammeter. So the ammeter reading is going to be equal to 2.5 times I. So that is 2.5 times I, which is 5 over 8.5. So this is going to give us 5 times 2.5 divided by 8.5, which gives us 1.47, which is 1.5. 1.470, which is 1.5. So the answer is A. I want to use the previous approach. I think there was just a small error. Suppose I say, now I'm using a different color for a different approach. Suppose I say the current here is I, and the current here will therefore be twice I. Therefore, the current here is going to be, if the current here is I, the current here is going to be 1 over 2I, and the current here is supposed to be 1 over 5I. Yes. When I multiply this by 2, I get the other one. But when I multiply this by 5, I get the other one. This by 2.5, I should be getting that one. So then I say I plus 2I plus 1 over 5I is equal to 5 amperes. That is by Kirchhoff's first law. So we got 17 over 5. I mean 17 over 10 is equal to 5. 17 over 10 I is equal to 5, where 10 I was 50 over 17. But then it means the reading of the ammeter reading is twice I. So the ammeter reading will be 2 times 50 divided by 17. So 2 times 50 divided by 17. 2 times 50, that is 100. I think this relation is not correct. When I multiply this by 2.5, No, I'll just leave this one because it doesn't give me a clear relation. 1 over 5. Oh, this is a half, which is 0.5. 1 plus 0.5 plus 0.2. 1 plus 0.5 plus 0.2. What is 1 divided by 5, which is 0.2? Okay, I think this relation will not work here because of the math. My mathematics may not be very good here. But this side, the blue one has worked directly. I think the blue one is easy. Something's wrong with my pen. It is not responding. Okay, so a simple analogy that we can take. So the current in 5 ohms should be 5 times the current in 1 ohm. But again, remember there should be a relationship between the currents in both. There should be a relationship between the current in 1 ohm and the current in 5 ohms. I mean in 5 ohms. That's why this is a clear relation. When I take this as 2.5 and I, there's a clear relation between those three currents. 4 resistors of equal value are connected as shown. So note that they are of equal value. Okay. If they're of equal value, then it means their resistances are identical. Let's say each of them is R. So the resistance here is going to be 0.5 R, even here it will be 0.5 R. How will the powers to the resistors change when the resistor W is removed? Let's first find the initial power. So if we know that the resistance, we have now seen the resistances, and we know that power is equal to I squared times R. So power is going to be equal to I squared times R. The power in each of these resistors will be the same because they are identical and the total resistance here is the same, so the PD is divided equally. So it means in series, our total resistance here is going to be 0.5 R plus 0.5 R, I think. So total resistance is going to be R here. So total resistance is R, so I can find the current. Let the EMF of the battery be E. The current is going to be EMF, which is E, over total resistance, which is R, if they are like that. So it means the power in X, I'll take the power in X alone, is going to be, note that this current E over R is divided equally because they are identical. So the total current is E over R. So it means X takes a half of that. So the power in the current in X is going to be E divided by 2R. That is the current in X. So it means power in X would be, for example, I squared, which I is E, divided by 2R, but this is squared, times the resistance of X, which is R. So this will be times R. So E over R, I remember, is I. So the power here will be a half I squared times R, which is going to be a half squared is a quarter. So this is a quarter I squared times R, because one R cancels out. Of course, this is 0.25 I squared times R. That will be the power. Because all the resistors are identical, the power through each, the power in X will be power in W, will be power in Y, and so on and so forth, to be 0.25. Now let's assume when W is removed. When W is removed, the resistance here will remain 0.5 ohms. I mean 0.5 times R, the resistance here will be just R. So total resistance now, I will change the color for a different, for when W is removed. So total resistance R total will now be R for X plus the total resistance here, which is 0.5 R, which means this will be 1.5 R. Now the current changes. The current is going to be the e.m.f over total resistance, which is 1.5 R. And 1 over 1.5 R, I think that is 2 over 3. So the current is going to be 2 over 3. Where there is E over R, I will put I. So it is 2 over 3 I. That is the new current. So if I try to find the power in X, remember, all this current here is going to go through X. So it means the power in X is going to be equal to I squared, which is 2 over 3 I, that is current squared. Remember, this is the all because there is no W, the current does not divide through X. It all goes through X. It only divides when it is entering Y. So it will be 2 over 3 I, but squared, then times the resistance of X, which is R. And this gives you, I think, 2 over 3, 2 divided by 3, but squared, that gives you 0.44 recurring. So this is 0.44 times I squared times R. So that is going to be the new power across X. You see that the power has changed from 0.25 to 0.44. So the power in X increases. Does it increase in all of them? So we have eliminated B because B is saying the power in X decreases. Does it increase in all of them? Let's check at least what happens to the current when it reaches here. 2 over 3I divides in n of these. So the current in Z is going to be half because the current divides at the junction. So it will be a half of 2 over 3I, which becomes 1 over 3I. So the power in Z, therefore, is going to be the current, which is 1 over 3I, but this is squared, times the resistance of Z. And I think 1 divided by 3, even if I square it, it gives me 0.11 recurring. So this is 0.11 times I squared, then times R. You see that the power across Z is now less than 0.25. And of course, the power across Z is the same as the power across Y because they're in parallel, the current divides equally, and they're identical. So it means also that the power across Y is also going to be 0.11 I squared times R. So you see that the power has actually reduced in Y and Z. So it increases in X, but it decreases in Y and Z, which means the most appropriate statement is going to be C. The power to X will increase, the powers to Y and Z will decrease. Okay. In the circuit shown, XY is the length L of a uniform resistance C, wire R1 and R2 are unknown resistors. J is a sliding contact that joins the junction of R1 and R2 to points on X, Y through a small signal lamp S. To determine the ratio V1 over V2 of the potential difference across R1 and R2, a point is found on XY at which the lamp is off. This point is at a distance x from capital X. What is the value of the ratio V1 over V2? So remember, PD is directly proportional to length. So it means V1, which is the PD across R1, is going to be a constant times the length corresponding to that balance point, which is X. Then when I transfer the lamp to this point here, it means the PD across 1 plus the PD across R2 should give us K. The balance length is now L. So if I want V2 alone, I will subtract the two equations. So V2 is going to be this equation minus the other one. So it will be K into L minus X. So the ratio is going to be equal to V1, which is Kx, divided by V2, which is K into L minus X. K is the PD per centimeter, or it is a constant. So this cancels, and our answer will be D. What describes the electric potential difference, that is V, between 2 points in a wire that carries a current? Electric potential difference is not a force. Energy dissipated between the 2 points to the current. Energy over current, that is not PD, so this is not correct. Power dissipated between the points to the current. Power divided by current, that is PD, so the answer is C, because we know power is equal to IV. A cylindrical piece of a soft electrically conducting material has a resistance R. It is rolled out so that its length is doubled, but its volume stays constant. If volume stays constant, remember volume is going to be cross-sectional area of the first one times its length. This should be called the cross-sectional area of the second one times the length L2. So let's find A2. Let's assume they said it has a resistance R, it is rolled out so that its length is double, but its volume stays the same. So it means A2 is the length is double. So let's say A1 times L1 is equal to A2 times twice. The length is double, so it is times twice L. So if the first one has length L, cross-sectional area A, then it means we can predict that A2 is going to be equal to twice, or it is going to be 1 over 2 of A. The length L cancels out, so A2 is going to be a half of A. So what is the new resistance? So let's come up with the two equations. Resistance is going to be rho L over cross-sectional area. That is for the first Y. For the second one, R2, resistance is going to be rho. The length is twice L. Cross-sectional area is a half of the other one, so it is a half A. So when I pull out 2 and a half, this becomes 2 over a half into rho L over A. And remember, rho L over A is R. So the 2 divided by a half is 4. Then rho L over A is R. So our answer is going to be D. A source of EMF has a constant internal resistance R and is connected to an external variable resistor R. As R is increased from a value below R to a value above R, which statement is correct? Remember in one of the questions that we saw, a graph of power against load resistance against the load resistance R. When R was increased from a certain value, let's say from 0, when it reached R, which R is internal resistance, the power was maximum. I mentioned that power is maximum when the load resistance is equal to the internal resistance of the battery. So the largest output power is obtained when the load resistance is equal to the internal resistance. So the answer is automatically D. Which statement is correct? The terminal PD remains constant, it doesn't. The current in the circuit increases when the variable resistor R is increased, the current does not increase, it decreases. The EMF of the source, it doesn't change. The largest output power is obtained when the load resistance is equal to the internal resistance. Which graph is best represents the way in which the current I through a thermistor depends upon the potential difference V across it? A thermistor. For a thermistor, we know that as temperature increases, the resistance decreases. But remember, I is equal to V over R. That means the gradient of this graph is going to be 1 over R. For a thermistor, as temperature increases, the resistance decreases. So when the resistance decreases, it means the gradient must be increasing. So this is showing decreasing gradient. This is showing constant gradient. This is showing the gradient is decreasing also here. So our answer is going to be A. For a thermistor, If I is equal to V over R, from the graphs which have been plotted, the gradient is 1 over R. But for thermistor, as temperature increases, resistance decreases. And when you go back to the expression for the gradient, as resistance decreases, the gradient increases. So you see this graph is showing an increasing gradient. Safety on rails is increased by using several electrical switches. Okay. Which law does not allow the green lamp to light? Which law does not allow the green lamp to light? Now I want you to note that as long as there is a complete circuit, the lamp will always light. So if P is closed and Q is closed, the lamp will light. If RS is closed and R is closed and S is closed, the lamp will light, even if P and Q are open. If R, let's see when it lights. I'm saying closed, both of them closed. Closed PQ, it lights. Closed RS, it lights. Closed RT, it lights. Suppose now we eliminate. Suppose we close R and we close P and R, or Q and S, and leave P and R, or we leave S and T. We leave S, T, Q, and we close P and R. Those ones will not light. It will not light. So let's check here. Which row does not allow the green lamp to light? Let's check the first row. The first row is showing P is closed, Q is closed, R. As long as two which lead to the lamp are closed, it will always light. And we see P and Q are closed. P and Q are closed. As long as those two are closed, the circuit is complete. That will light. P and Q, P is closed, Q is open, R is closed, S is closed. Note that if R and S are closed, the circuit is complete. It will light. P is closed, Q is open, R is open. As long as there is an open switch above and below, then this one means it will not light. There is an open switch in the upper loop and an open switch in the lower loop. It will not lamp. It will not light at all, unless the open switch is T. But if S or R are open and there is an open switch up, then it will not light. Then they open, P is open, Q is open, but R is closed, S is open, but T is closed. It will still lamp. When I close R and close T, the circuit is again complete. So the answer here is going to be C. It will not allow the green lamp to light when P is closed, Q is open, R is open, S is closed, T is closed. The diagram shows a fixed resistor and a light-dependent resistor in series with a constant low-voltage supply. When the LDR is in the dark, the fixed resistor and the LDR have the same value of resistance. Okay, we have seen a similar question. Light is shown on the LDR. That means the resistance here decreases. So PD across the fixed resistor increases because the PD across the LDR decreases. What happens to the potential difference across the two components? For the fixed resistor, we have said it increases. For the fixed resistor, it is increased. Automatically for the LDR, it is decreased. So the answer is going to be B. The diagram shows a DC circuit. What is the resistance between points P and Q due to the resistance network? Now, these two are in parallel. I said whenever you have two identical resistors in parallel, their total resistance is half of the resistance of just one. So you can predict that if I have 6 and 6, the resistance here is going to be 3 ohms. Now I have a resistance of 6 ohms here. And I have another resistance here, which is 3 plus 3, which is 6 ohms. And these are in parallel now. This is where we have P and we have Q the other side. Again, we have 6 ohms in parallel. They are identical, so the resultant is 3 ohms. How am I arriving at 3 ohms? Whenever I have two resistors in parallel, the resultant resistance is a product of a sum. So 6 times 6 over 6 plus 6, this gives you 3 ohms. So our answer is going to be C. Which statement about resistivity is correct? Resistivity. So we know the resistance is equal to rho L over cross-sectional area, or resistivity is equal to R times A over length. Okay. The resistivity of a material is numerically equal to the resistance in ohms of a cube. A cube that is L is 1 meter, area is also 1 meter squared. A cube of the material that the cube being of side length 1 meter and the resistance being measured between opposite faces. So the answer is going to be A. Resistance in ohms, cube being of side 1 meter, it means the area is 1 meter squared. The length is 1 meter, so the answer is A without wasting any time. Which of the equations that link some of the following terms is correct? I think we have answered a similar question. We checked all these equations and we noticed that the last equation, power is equal to EI over Q, was the one making sense because charge is I times T. This gave us energy over time. Energy over time is joules per second, which is power. So the answer was D. Which statement is not valid? Which statement is not valid? Current is the speed. Current is not the speed of charge. Current is, they said not valid. Current is the speed of charged particles that carry it. So current is not the speed. So that statement is not valid. EMF, energy converted from electrical to other forms. That is true. PD, between 2 points, is the work done in moving unit charge from one point to another. That is PD. Resistance between 2 points is PD per unit current. That is V over I, which is correct. A cell of EMF E and internal resistance R is connected in series with a switch S and an external resistor of resistance R. The PD between P and Q is V. When S is closed, assuming S is closed, V decreases. Yes, it is true, V decreases. The PD between P and Q is V, that is the terminal PD is V, it decreases, that is true. So first eliminate is C and D, because C and D are saying it remains the same. It decreases. But why does it decrease? V decreases. It decreases because there is a PD across R. That is not the reason as to why it decreases. It decreases because there is a PD across the internal resistance. They are lost volts, so that is V. Remember, PD is equal to the EMF minus the lost volts. Lost volts is the PD across the internal resistance, which is small r. This makes this one to reduce. A cell, two resistors of equal resistance and an ammeter are used to construct 4 circuits, and the resistors are the only parts of the circuit that have resistance. It means the ammeter has 0 resistance. In which circuit will the ammeter show the greatest reading? So here the resistance is twice if the resistors are identical. So there is a current here, but there is a resistance here. We just check the resistance. Here it is twice R. Here the ammeter will only will only experience a resistance which is R, because current will not go through this one. It will just go through the ammeter and take this route, or it takes this route through the ammeter. Then here, when current comes, part of it, current divides at the junction. That means a small current takes that route. Although the current here may be greater than the current here. No, the current here is more than the current here because here it divides. Then here, the battery is in this point. It means all the current in the circuit goes through the ammeter. Therefore, this one will give the greatest reading. So the answer is going to be D, because the ammeter is in series with the battery and there's no resistance here along this branch. That means all the current goes through the ammeter. Therefore, this will give the greatest reading. In this one, the ammeter shows the greatest reading. And lastly, for this part, Three resistors of resistance R, 2R, 3R are connected in parallel. Okay, they are connected in parallel. Using I to represent the current through the resistor of resistance R. So this current is I. If that one is I, this one should be a half of I. And if that one is a half of I, this one should be 1 over 3I. 1 over 3I. So using I to represent the current through the resistor of resistance R, which row represents the relationship between the currents through the resistors? So in R it is I, it goes on reducing depending on the ratio of the resistances. So in R it is I, in 2R is going to be a half I, in 3R it is going to be a third R. So where it is where the resistance is R, we have seen it is I. Then in 2R should be a half I, in 3R should be a third I, so the answer is going to be B. Okay, so that marks the end of this episode, and see you in the next episode. Have a blessed evening. Bye bye.